everyone, thanks for tuning in today for Sharon's special update on voice production. I thought it would be helpful to have my friend Mr. Larynx join us today. Before I jump into the components of voice production, let me introduce you to Mr. Larynx. He plays a vital role by protecting the airway, assisting with regulating breathing frequency, and compressing and holding air in lungs during various activities such as lifting. He consists of a hyoid bone right here, the epiglottis, and multiple cartilages, which include the thyroid, the cricoid, two arytenoids, along with the creniculates, and also the cuneiforms. There are also intrinsic muscles of the larynx, which are the interarytenoid muscles right here, both transverse and oblique. And then we have the lateral cricothyroid muscles right here. And then we also have the posterior cricoid muscles here in the back. And then we have the thyroarytenoid muscles right here in the inside, the O. And then we also have the cricothyroid muscle, which is right here. Here are the three membranes. We have the thyrohyoid, and we have the cricothyroid, and then the cricotracheal membrane. You can also see the first tracheal ring right here. Other structures include the cricothyroid joint, which is right here. And then we also have the other joint, which is the cricoarytenoid joint, which is right here. In addition, here are the epiglottic flows, aerial epiglottic flows right here. And then we also have the superior and recurrent laryngeal nerve. Now let's talk more in detail about voice production. I have received a lot of questions about how does respiration relate to voice production. Respiration is an essential component for voice production. The exhalation that takes place during the respiratory cycle for voice production is what drives the vocal fold production. There are necessary and sufficient conditions for phonation, which include having laryngeal adduction, and the arytenoids have to be pulled together so that the vocal folds are together in a pyramidal position. There also has to be medial compression of the vocal folds with some longitudinal tension. Then we have to reach enough subglottic pressure in order to cause the vocal folds to be blown apart. And it is the production of the subglottic pressure where respiration is essential. So the directory component is that during exhalation, the muscles of exhalation along with the elastic recoil forces of the lungs cause a decrease in the volume of the thoracic cavity, which drives up pressure. That is how we generate pressure. Relative to respiration to voice productions, the muscles of exhalation along with elastic recoil forces of the thoracic cavity and the diaphragm return it back to its normal resting position and all decrease the volume of that cavity, which results in an increase in pressure until we reach phonatory threshold. You had an opportunity to see the intrinsic muscles earlier. Let's discuss the function of these muscles. So there are a set of adductors, and these are the lateral cricoarytenoids, and that's what we went over earlier, the lateral cricoarytenoids, and the interarytenoids. The interarytenoids, right here, transverse and oblique fibers of the arytenoid muscles, they cause the arytenoids, right here, to come together, slide across the top of the cricothyroid cartilage, and are rotated so that the vocal processes are also rotated together to bring the vocal folds are in here, together. The lateral cricoarytenoids, right here on the sides, they pull on the muscle process and pulls it anterior and inferior, which also causes the rocking and rotation of the arytenoid cartilages, so that the vocal processes are brought together. The posterior cricoarytenoid muscle is an abductor. Therefore, it opens the arytenoids, right? It opens the arytenoids by pulling back and down on the muscle process to abduct the arytenoids. The vocal tensors are the pars recta and pars oblique fibers of the cricothyroid, which is the primary mediator of pitch. It causes a decrease in the distance between the anterior thyroid and cricoid cartilage, which stretches the vocal folds, therefore leading to an increase in pitch. The thyroarytenoid muscles, as I said, these are in here. The thyroarytenoid vocalis forms the body of the vocal folds. The thyroarytenoid muscularis attaches to the muscle process lateral to the vocalis. You may have wondered how the cartilages move relative to each other and the effect each may have on the vocal folds or voice production. When the interarytenoid muscles contract, it causes the arytenoids, right here, to move closer together, and they slide along the top of the cricoid cartilage, which is right here. The lateral cricoarytenoid pulls forward and down on the muscle process, rotating the vocal process in. The cricothyroid causes the thyroid cartilage to rock forward on the joint, with the cricoid increasing the distance between the anterior and posterior attachment of the vocal folds. So what about the nerve supply to the intrinsic muscles? You might ask. The vagus nerve that supplies everything laryngeal and all of the intrinsic muscles of the larynx receive the nerve supply from the recurrent laryngeal nerve, that is all the intrinsic muscles of the larynx except for one, which is the cricothyroid, and it receives its supply from the superior laryngeal nerve. Both branches are part of the vagus nerve. Have you heard of the myoelastic aerodynamic theory of phonation? Well, let me tell you about it. This theory states that once the necessary sufficient components for phonation are achieved, that's adduction, medial compression, longitudinal tension, and subglottal pressure, sufficient to reach phonatory threshold. Once those things are in place, phonation begins, and that the phonatory threshold causes the vocal folds to part. Then air rushes through the glottal space. When that happens, the Bernoulli effect on the vocal folds is such that there is an increase in the velocity of airflow through the glottis, while there is a decrease in pressure against the size of the restriction, or in this case, vocal folds. When there is a drop in pressure against the size of the vocal folds, there is no longer sufficient pressure that drop against the vocal folds, which causes enough of a decrease in pressure that the vocal folds are no longer held open, and that drop sucks the vocal folds back together. Once that occurs, as long as there continues to be subglottic pressure, it builds back up. As soon as the vocal folds close, the pressure builds back up, blows the vocal folds apart. Bernoulli effect essentially sucks them back together again, and the process repeats itself 100 to several hundred times per second. Once that cycle of oscillation or vibration of the vocal folds is set up, what we have is the mucosal wave, such that the soft, pliable tissue is blown apart from inferior to superior. If we see the vocal folds in slow motion, they appear to undulate with the wave of tissue from the inferior or bottom lip of the vocal folds up and across the top and across the horizontal shelf of the superior surface. So the mucosal wave is simply the movement pattern of the vocal folds during phonation. Our time is up. Thanks for joining today's special edition for an update on voice production.